Final example, the volume of a spherical balloon is given by volume equals 4/3 pi r cubed. The balloon starts being inflated at time t equals 0 in seconds, and its radius in centimeters is given by r equals 3 times the square root of t. Okay, wait, so what does that mean? Let's try to figure it out real quickly. So we've got a spherical balloon. Well, a sphere is just a ball, right? So that's basically what we expect when we think of balloons. So this is making sense, right? And it's being inflated, it's being blown up, and at time t equals 0, so that's just when we start, its radius is given by r equals 3 root t. So it starts at t equals 0, and what is its radius at t equals 0? R equals 3 root t, so 3 times square root of 0. Oh, so its radius is 0. So it starts off completely small, it's completely uninflated, it's just a dot at 0. And then from there it inflates, so it grows out from that point. It grows out from that moment in time. Give the volume of the balloon as a function of time. So we blow into the balloon and the radius expands and the radius expands and the radius expands. And as the radius expands, there's now volume inside of the balloon. What is the volume at 30 seconds? All right, so first thing we need to do is we need to give the volume of the balloon as a function of time. Well, first off, we might want to see these as functions, because right now, v equals 4/3 pi r cubed, r equals 3 root t, they're not actually functions right now, but we could easily turn them into functions. So volume is really just a function of radius, because the only thing that can vary in there is the radius. So it's 4/3 pi r cubed. Simple function. And then what about radius? Well, radius is a function based off of time, because the only thing that can vary in it is time, 3 root t. So the volume of the balloon is a function of time. Well, volume of the balloon doesn't have time inside of it. But we do know that volume has radius inside of it. And radius has time inside of it. So we can just put these together. We can compose them. And volume of radius of time will be equal to a function based off of time that will give the volume of the balloon. So let's see what that is. Volume of 3 root t. Oh, hey, now we're just plugging in the radius at any given time, and that's going to be volume of 3 root t. So if we plugged in our box for r, that gives us box here cubed times the other stuff. So it's going to be 4/3 pi times quantity 3 root t cubed. We simplify this out a bit. We get 4/3 pi times 3 cubed times the square root of t cubed. So notice, 3 cubed, well, that can cancel down to a squared and knock this guy out. So we've got 4 pi times 3 squared. Well, 4 pi 3 squared, hey, what is 3 squared? 3 squared is 9. 4 times 9 is 36. So we've got 36 pi. What about root t cubed? Well, remember, root t squared, let's put in a different color so we don't get it confused. Root t squared would just be equal to t on its own. So root t cubed is just one extra root t left over. So that gives us times t root t. And there we are. This is the volume of this balloon, volume of radius of time, but it's also a way of seeing volume that's purely in terms of t, right? T shows up, but pi is a constant, 36 is a constant. So what we've got now is we've got volume based purely off of time. We've got the first part of this question done. Next part, volume at 30 seconds. Well, we've got two options for how to do this. We could plug in into the function that we just built. Volume at 30 equals 36 pi times 30 times square root of 30. Or we could plug in volume of radius at time t, which would be volume of 3 times square root of 30, which would be equal to 4/3 pi quantity 3 root 30 cubed. And it winds up being the case that these two things actually wind up equaling the exact same thing. So let's just fold them together. So 36 pi times 30 times root 30, that winds up equaling 1080 pi square root of 30. And if we want to get this as an approximate value, something that we could actually know a number as opposed to just having symbols that are precise and accurate and exactly correct and right, but hard to actually grasp as a single number and know what we're talking about, we could get a pretty close thing, and we could round this to 8,584 using a calculator. What's the units that it comes in? Well, it's centimeters cubed, because if radius is in centimeter and volume is centimeters cubed, and it makes sense because we're talking about volume, and length is centimeters, area is centimeters squared, and volume is centimeters cubed, at least if we're using centimeters. If we're using meters, it's meters, meters squared, meters cubed. If we're using inches or feet, it is square inches, square feet, and cubic inches, cubic feet. All right, great. That completes it for composite functions. I hope you have a much better understanding of what's going on. Remember, when you see that circle, it means composed with, but it's much easier to break it into f of g of x, or g of f of x, depending on the order it goes in. And remember, it's just going to be based off of the order that they're hitting the x in. Whoever's closer goes first, so this becomes f of g gets to act first because it's closer to the x. That's what that means. Whoever's closer goes first, so it's whatever the order is with the circles, but now f of g of x. F circle g x becomes f of g of x. A circle b circle c of x becomes a of b of c of x. Great. All right. Glad to have taught you the composite functions. Hope you can use it in a bunch of places. It will show up in a variety of things. Really useful stuff here. And we'll see you at Educator.com later. Bye.